Hello everyone, Mr. Minix, my name, math is my game. I'm looking at my talk box, my TC Helicon Perform V, and it's not set up on the alien voice, so that's good. So today, chapter 4, section 9 with Algebra 2, here it is. Quadratic systems. This is it. This is the end of the chapter. If I had used the other textbook, I think they split this section up into two. They do quadratic systems and then quadratic inequalities. So I'm going to kind of mash those two up together into one. So if you remember a system of equations, by definition is two or more equations using the same variables. So in this class, we kind of skipped a little bit dealing with the systems, but we did look at a couple linear systems and we solved them with matrices. But if we had something like y equals x minus 7 and y equals negative 2x plus 1, if we had something like that, we could probably solve that by graphing. Is one technique we could use to solve that. We could, graph that system. Try to get this going here. So if I look at this first equation, oh man, it's going to be a long day. If I look at this first equation and I wanted to graph that, slopes 1, y-intercepts negative 7. So the graph of that's going to look something like that. I'm just really quickly sketching these. And the second equation, if I were to graph that, negative slope, y-intercept a positive 1. It's a little bit steeper, so it's going to do something like that. And our solution, our answer, would be that ordered pair where they meet, right? So we're going to be doing the same kind of thing, but this time not with linear equations, but with quadratic equations. Okay. So one question in here, this is a freebie. It's not that often that I give freebies out, but I have been in a generous mood lately. On your Chapter 4 test, here's one of the questions. Explain the number of solutions a quadratic system could have. Explain the number of solutions a quadratic system could have. So what you've got to be able to do here is think to yourself, what could a quadratic system of two or more equations, and usually they're two, but if I were graphing two quadratics, what could that look like? Oh, this is lovely. Can't add the attachment to my, oh great. All my nice little attachments in the side toolbar and I can't add them because this is the trial software, whatever. All right. So here we go. I might have a parabola that looks like this and another parabola that I'll use the same color, another parabola that looks like this. So that might be one instance of a quadratic system. How many solutions does that have? That doesn't actually have four solutions. The solutions are where the lines meet. Two. The two solutions would be that point of intersection and that point of intersection. Okay, so two solutions is one of the answers to this. All right. Is this making sense so far? A little bit? Okay, cool. So let's try another scenario then. And this is the thing you got to be able to kind of picture in your mind, or maybe you even want to sketch them out. So maybe I have a parabola that looks like this, and another parabola that looks like this. What do you think about that one? Yeah. That has no solution because they don't meet. The two things don't meet. So a quadratic system could have two solutions. A quadratic system could have no solutions. Are there any other possibilities? Or is that it? You thinking one? Well, what's that going to look like, one solution? Is it possible to have a quadratic system with one solution? If we had a graph that looked like this, and an upside down one, and they just kind of meet in one spot like that? Okay. So it is possible that quadratic systems could have one solution. Now, one thing we had seen when we studied lines is sometimes the lines overlap, right? Is that possible with parabolas also? Sure is. Sure is. What if we had something like y equals x minus 3, the quantity squared, and y equals x squared minus 6x plus 9? If we had something like that, well, we'd have infinitely many solutions because the first equation here has a vertex of 3, 0, 3, 0, and it opens up like that. And the second equation has a y-intercept of 9, and if we were to factor that down, it's the same thing as the other one. It's the same thing as the other one. So that particular system could have infinitely many solutions. So that's a test question that you're going to see on Thursday's chapter test. Explain the number of solutions a quadratic system of equations could have. Could have no solution, could have one solution, could have two solutions, or it might have infinitely many. How we doing? So now that we kind of have an idea of what it is we're looking for, I guess we'll go ahead and try. We've got three examples of, I don't even know if we need to go through three. Probably an example of a quadratic with a linear, an example of a quadratic and a quadratic, and then we're going to flip it and we're going to look at some inequalities after that. So, ready? All right. So example number 1. Solve this system of quadratic. Well, this is actually going to be a linear and a quadratic. Y equals x squared plus 6x plus 9, and y equals x plus 3. Okay. So if we wanted to solve this, we could do this a number of ways. We could use graphing, and actually might not be a bad review of graphing for this. Oh, that's right. I can't use that. Dang it. That's okay. I'll make do with what I got. So if I wanted to graph this line, I know its y-intercept is 1, 2, 3. So it's going to go through the point 0, 3. And I know that this line's slope is 1. So the thing would go through the point 1, 4, 2, 5. Maybe I'll put that stuff off to the side. 1, 4. Well, let's see. 1, 4, 2, 5, 3, 6, 4, 7. 1, 2, 3, 4. Probably good enough. All right, and then this other equation, this quadratic, that factors into x plus 3, the quantity squared. Factors into x plus 3, the quantity squared. So that means it's going to be translated 1, 2, 3 units to the left. So its vertex is at 0, negative 3. And if I go over 1, I'd go up 1. And I think that might be one of the solutions there, I think. With the line, I could keep on going back the other way. I could go to negative 1, 2. And I think that parabola goes to the same point, right? Is that right? Negative 1, 2? Seems like that's one of my answers. Seems like that's one of my answers. Everybody picking up what I'm putting down here? Okay. And with that line, maybe I should go back one more time with that line. Over 1 and down. Whoa. Yeah, there it is. There's the other solution with that line. So the other solution would be 0. Oh gosh, I got it wrong. I can't believe nobody said anything. That's a Monday. I'll let it slide this time. What's wrong with the way I labeled the vertex? I put the lime in the coconut. Isn't the vertex negative 3, 0? So then our other solution here would be negative 3, 0, right? And I think I even got that other point twisted. That negative, um, that's actually negative 2, 1. Oh my gosh. That's negative 2, 1. And that's negative 2, 1. Oh well. Hopefully we get the idea there. I'm sorry about being confusing and lost and labeling those things wrong. Maybe I need to take a swig of coffee. Well, I'm not going to be like the hipster. You heard about the hipster, right? The hipster drink. Well, the hipster burnt his mouth really severely because he drank coffee before coffee was cool. My coffee is cool. It's cold. It's a day old. It's Dunkin' Turbo, so maybe that'll help. So maybe you don't like graphing. Maybe you mislabel points when you graph like I did. Can somebody think of a quicker way to solve this? A more effective way to solve this? Let's think about what class we're in. Algebra. So why don't we use algebra? In geometry, you studied these properties, and one of them said that something is equal to itself. The property that said that A equals A. You remember that one? That's not the identity. It's the reflexive property, right? Well, isn't it true then that Y equals Y? And by the identity, I'm not the identity, not by the reflexive property and by substitution and by the reflexive property, we could say that the two Y equivalents, this x squared plus 6x plus 9, is equal to the other one of x plus 3. Does that make sense? Good. All right, so I guess now we got that to solve. So I would probably subtract x from both sides. So x squared minus 5x, and I'd probably subtract 3 from both sides. That plus 5x. Thank you. Good looking out. Maybe I need to take some more of that turbo down. And then that's going to be plus 6, and that's equal to 0. So at this point in time, this close to the chapter test, I really hope and I really pray that everybody in this class could solve that. And they know the best way to solve that. On Thursday's test, there's going to be a question like that. Which method would you use to solve that? Factoring. Thank you. Good. Why would you factor it? Because it's simple to factor, right? Because 6 has got factors it out up to 5. Good. So x plus 2, x plus 3 equals 0. So x plus 2 equals 0. X plus 3 equals 0. So x equals negative 2. X equals negative 3. And you might think we're done. Well, if you stop there, you left the milk in the car. Yeah, we have to solve for the corresponding y's also, right? Because when we solve a system, it's where the things meet, and the things meet at a point in space. And there's a fly on my smart board, so flies have been hanging out all over the place today. All right, so I know one of my answers is negative 3. So I would probably use this equation here to find my y's. Okay, so we know that y is x plus 3. So the y value is going to be negative 2 plus 3, which is 1. So negative 2, 1's our one answer. Y equals negative 2 plus negative 3. Hold on a minute. Did I do that right? Oh, no, I did. Man, I just need to slow down, and maybe I drank too much of that coffee. Y equals x plus 3. So that's negative 3 plus 3. So that's 0. So we got the point negative 3, 0 then. So those are our answers. Those are our 2 points where these graphs undoubtedly meet. How do we feel about that? All right. What technique do you think is easier, the algebra way or the graphing way? I think the algebra way is a lot easier, huh? Cool beans. Well, that's an example where we had a line and a parabola, and there was 2 solutions. So let's look at one where there's 2 parabolas. 2 parabolas. So we'll go ahead and call this example 2. Example 2, solve this system. Y equals negative x squared minus 3x plus 10, and y equals, oh man, I wrote the wrong one. I'm sorry. You probably already wrote that down in pen too. Y equals x squared minus 4x plus 5. X squared minus 4x plus 5. And y equals negative x squared minus 5. Sometimes I like to just sketch these things before I go ahead and solve them. Sometimes I like to get just a rough estimate as to whether these things actually are going to meet before I try to do any kind of algebra. So if I look at the first one, I know the y-intercept's 5. I know the vertex is going to be 2 something. It's probably going to look something like that. And if I look at this second one, its y-intercept's negative 5. Its y-intercept's negative 5, and it has an a value of 1. I don't know. These things might not meet, right? Maybe they will, maybe they won't. Who knows? So how are we going to find out? Yeah. We could put it on the calculator and graph, but suppose we don't have one. We're going to try some algebra? All right. So what are we going to set equal to what? X squared minus 4x plus 5 equals negative x squared minus 5. Good. So then we'll probably want to combine our like terms, so we'll go ahead and add x squared to both sides. So we get 2x squared minus 4x, and then we'll probably want to go ahead and add 5 to both sides. So plus 10 equals 0. Oh, good. Factor a 2 out. 2, 4, and 10 are all even, so yeah, we'll factor a 2 out. So 2, 4, and 10 are all even, so we'll go ahead and factor a 2 out. So that's 2 times x squared minus 2x plus 5, and that equals 0. All right. So there's a really huge idea coming up here, and I hope somebody has the foresight to think about it. I hope somebody in here has the foresight to think about what two things I'm going to, well, first of all, what I'm going to notice, and then what I'm going to do to even see if there's any real answers. Does 5 have factors that add up to 2? No, so we can't factor. So factoring's out. That doesn't mean there's not answers, though. But factoring is out because 5 has no factors that are going to add up to 2. So who could tell me what idea I'm going to apply here to see if this thing even has any real answers? It's from 2 sections ago. Chapter 4, Section 7. What about the quadratic formula? There's one part of it that was new this year. Solving the squared. Well, there's something under the radical that we're interested in. Anybody remember the name of that? Chapter test is coming up in 2 days. Better know it. If it's positive, then one thing happens. If it's negative, then something else happens. And if it's 0, then, oh gosh, that thing. The discriminant, the discriminant's the b squared minus 4ac, right? So before I go even solving this, I'm going to check the discriminant. I'm going to see what the discriminant is. So b is negative 2, so this is negative 2 squared minus 4 times a, my a is now 1, times c, my c is 5. So that's going to be 4 minus 20. Well, what's the difference between 4 and 20 and the 20 is negative? It's negative 16, right? So what's that tell me about this equation? That it has no real solution. So what do I know about the system then? That it's not going to have a solution, okay? So the answer to this then is no solution. This has no solution. Now, somebody mentioned let's graph it, and let's graph it. Let's just confirm this on the calculator. So we got x squared minus 4x plus 5. And I want to graph that. X squared minus 4x plus 5. So there's the one graph, and I'll add the next one on the same graph. Negative x squared, take away 5. Wow, yeah, it's pretty clear there that those things don't even come close to intersecting, right? How we doing? Yeah, question. So if you're talking about systems, it doesn't really make, there are imaginary solutions, but it really doesn't make sense to even find them, because when we solve a system, we want to know where the things meet. But that's an excellent question. If we were solving a quadratic equation at this point in our math class, we would be asked to find the answers, but in the context of a system, we want to know where do those lines overlap or meet. Good question. Any other questions before we look at our next two examples? All right. So I know it's been a long time since you've graphed an inequality, but that's what we're going to look at next. Example 3, we're just going to go ahead and we'll say solve by graphing. Solve by graphing. And unfortunately, because my smart board is not being cooperative today, I won't be able to have real nice graphs, but you'll get the idea. You'll get the idea. So here's my x and y axis. X, y. And I'm going to use two different colors for each equation, or inequality, I should say. So the first one's going to be y is strictly less than negative x squared minus 9x minus 2. And then my other inequality is going to be y is strictly greater than x squared minus 2. So there is one thing that I notice about both of these. They're inequalities, which are different than equations. If you remember, this means less than, but not equal to. So that means we're probably going to have to do some kind of shading. And it also means when I sketch my graph, I'm not going to have a contiguous line. I'm not going to have a line. I'm going to have a dotted or a broken or a hyphenated line. Does that make sense? Okay, so when I go to graph these parabolas, like the red one that happens to open downward, I want to use something like this, right? And when I go to graph my blue one, same thing. It opens upward, and I want to have a broken line because x is or y is not equal to. Okay, now I got to figure out where these things go, and if I look at the red one first of all, I see its y-intercept is negative 2. So maybe it's here, maybe it's here. I don't know. So I probably ought to find its vertex. And its vertex can be found by taking h is negative b over 2a. So that's minus 9 over 2 times negative 1. So that's 9 over negative 2. So that's negative 4.5. So negative 4.5 is kind of where its axis of symmetry is, I guess, if you want to think of it that way. Negative 4.5. And its y-intercept is negative 2, so I don't know where it's what its y-coordinate of its vertex is. Let's see. K is 4ac minus b squared over 4a. So that's going to be 4 times negative 1 times negative 2 minus negative 9, the quantity squared. That's all over 4 times negative 1. So that's 8 minus 81 over negative 4. So that's negative 73 over negative 4. So that's going to be like 16, 17, 18. That's 18 and 18 and a fourth, I think. Wow. Who picked these examples? I guess I did. Wow. So maybe this red thing I sketched here, maybe that needs to get out of the way. So my y-intercept is negative 4.5, negative 4.5, 18 and a fourth. And the y-intercept was negative 2. The vertex is negative 4.5, 18 and a fourth. So if I'm sketching that red thing, with a broken line. It's not going to go through 0, -2. It's not going to go through this point, but that's kind of like where its vertex is. So it's going to do something like this. And that less than tells me that I need to shade where with respect to all that stuff, above or below. What's the less than mean? Shade above or below it? Below it. So I'm going to go ahead and get out my red crayon. I'm going to use my red crayon. So I'm shading below that one. And then I got to graph this blue one. The blue one's going to be a lot easier to graph. The blue one that has a vertex of 0, -2. Hey, 0, -2. And the blue one's going to open up. And we know how the A value works. So the blue one's going to look something like that. And with the blue one, am I going to shade above or below that one? Above that one. Good. So I use my blue crayon. So I'm shading above the blue one. And my answer is going to be wherever those two graphs overlap. Can you see where they're going to overlap? It looks to me like there's going to be a sliver. Let me see if I can get my purple going. It looks to me like there's going to be a sliver right in there where those are going to overlap, right? So my answer is every single point that's in that zone, in that region. And honestly, to solve that by graphing, you just have to graph it and kind of point to that region and say, hey, my answer is any point in there. How many points are in there, by the way? Well, there's more than 2. There's an infinite number. Because even though it's a very small interval, even though it's only from here to here, we could find an infinite number of points in between those points. Kind of hard to wrap your mind around, but it's true, theoretically. So this is where the TI Inspire could be of assistance. So on the TI Inspire, I'm going to insert a new problem and a new graph. So watch what happens when I back up from the equal sign. I'm going to back up, and there it is. Y is less than -x squared minus 9x minus 2. So there's that one. And you'll notice that it even made the line broken. That's kind of cool. And my other inequality is that y is greater than x squared minus 2. And there it is. Get the idea? Questions, comments, concerns? All right. Well, we got one last example then. This last one, honestly, I think there's going to be a couple of these on the chapter test, the calculator Scantron chapter test. I think there's at least one, maybe 2 of these. And there's one of these that I put on the back side of tonight's exercises. Solve x squared plus x is strictly greater than 4. So this is a quadratic inequality, and solving it's kind of weird. I'll just briefly jot down the few things. Number 1, find the critical values. Number 2 is to determine the interval for the solution. And once you determine the interval that the solution's on, then go ahead and write your answer or write the solution. So you're probably saying to yourself, what the heck's a critical value? Well, critical value is simply a solution to the related equation. So if you pretend for a minute that this is an equation and you solve it, you'll find your critical values. So rather than working with a quadratic inequality, because that's scary, let's just pretend for a minute we've got x squared plus x equals 4. So here you go, another chance to practice for Thursday's test. What technique would you use to solve that equation? Factoring? Let's try to factor it. Does 4 have factors that add up to 1? Which ones? Remember, with solving quadratics, we could take square roots, we could factor, We could use the quadratic formula. We could complete the square, or we could try graphing. 4 doesn't have factors that add up to 1, does it? So factoring's out, so we can't factor this. Graphing it, the vertex is going to be on a fractional part, so I'm probably not going to try graphing it. Completing the square, my b value is not even, so I probably wouldn't complete the square. Can we take square roots on this? No. Some people want to try to do this. You can't do that. Okay, so taking square roots is out. So really that only leaves the quadratic formula. So here we go. Before I can do that, I got to have x squared plus x minus 4 equals 0. So x is negative b plus or minus the square root of b squared minus 4ac all over 2a. So that's going to be negative 1 plus or minus the square root of 17 all over 2. So those are my critical values. Wow. Square root of 17 is a little bit bigger than 4. So if I had negative 1 plus something a little bigger than 4, that's going to be like 3 something. And that's divided by 2. And 3 divided by 2 is like 1.5. So if I'm picturing this, here's 1, here's 2. One of my critical values is right about here. My other critical value would be negative 1 minus something bigger than 4. So that's going to be something a little bit bigger than negative 5, well, in absolute value. And negative 5 divided by 2 would be negative 2.5. There's 1, there's 2, there's 3. So my critical values are pretty much there and there. Does that make sense so far? Okay. So what I got to figure out then is my answer going to be in between those critical values, or is my answer going to be beyond those critical values? It's either going to be in between them or beyond them, and I got to figure it out. There's a real quick way to do this. Yeah. Do what? If it's greater than, will it be beyond? That's a good, if we were dealing with absolute values, that little trick would work. But we're not dealing with absolute values. We're dealing with quadratics. But there is something that we could do. There is some x value that we could quickly check to see if it satisfies the original inequality. What would be a nice x value to test? That's right in the middle, kind of, close. 1, we could test 1, but I could think of something even easier than that. 0. Let's plug in 0 for x to try to determine the interval. So x squared plus x is greater than 4. X squared plus x is greater than 4. So we're going to test 0. We're going to test 0. We're going to test 0. So what I'm going to do is I'm going to plug in 0 and ask myself, self, is 0 squared plus 0 greater than 4? Self, is 0 greater than 4? It's not. So what's that mean about my answer with respect to the critical values? It means my answer is not here, right? So what's that mean? Not no solution. The answer's beyond those critical values. Okay, so what I would have to write then is that x is greater than negative 1 plus rad 17 over 2. X is less than negative 1 minus rad 17 over 2. And I probably ought to have a word in between those two things, because it's like when you go for a ride in the boat, what you need to bring with you. So there it is. There it is. What do you think? Got it? There is another way that you could determine where your solution set is. I would probably write this as x squared plus x minus 4 is greater than y, so y is less than x squared plus x minus 4. So I would be graphing some kind of parabola, and with that parabola I would be shading on the outside of it because it's less than, and that's how I would have figured out that interval. But that's how I do it. It's been real. It's been fun. I hope everybody studies for the chapter test and has the best day of their lives. I'm going to give a shout out to the future Mr. Minnick, and I'm going to give a shout out to Dunkin' Donuts Turbo Coffee. Good.